Good day everyone, we are from Group 8. We will be presenting for our Six Sigma project. Our topic is Enhance Renewable Energy Efficiency in Malaysian Universities, which is related to SDG 7. Here is our group members. First of all, let me introduce myself. My name is Kwame Heng and my matrix number is MA23031. Now I will start our presentation with the introduction. Enhancing renewable energy efficiency in Malaysian universities is aligned with Global Vision of Sustainable Development Goal 7, which is affordable and clean energy, aims to ensuring access to reliable, sustainable and modern energy for all. Currently, Malaysian universities rely heavily on electricity from national grid, with around 15% of that energy generated from hydropower. While this provides a renewable energy source, many challenges handle its effective use within university campus. Key issues include outdated infrastructure, the absence of smart energy management system, and poor monitoring of energy consumption pattern.
Okay, next for project charter, project name Enhancing Renewable Energy Efficiency in Malaysia. This project is about improve the efficiency and reliability of renewable energy system in Malaysia University. The goal is to address operational inefficiencies and high maintenance costs, targeting improvement in energy operability and cost reduction within 6 months. So we are focused to improve the operational efficiency and cost effectiveness. Our project scope is to identify and eliminate the defect on turbine operation and design, and also improve the efficiency of reliability renewable energy system. This is about a problem statement that Malaysia University have challenged. Okay, next is our target. Our target is to achieve 10% improvement in energy output ability and achieve 15% reduction in maintenance costs within 6 months. Next is our timeline. We start define phase on 16 December 2024 and measure phase 30 December 2024, and this we start analyze, improve and control. Okay, next is our team member. So for financial, we have budget summary for training and consultant, system analysis and diagnostic, turbine design improvement, monitoring equipment.
Alright, I will present critical quality tree CQT. So CQT, it has need, quality driver and formal requirements. So our need is operational efficiency and high maintenance cost for exciting hydropower setup in Malaysian University. So it has 7 quality driver. For the first quality driver, hydropower turbine operational efficiency, and the performance requirement for hydropower turbine operational efficiency is increased turbine operational uptime to 95% within 6 months. So for the second quality driver is maintenance cost reduction. It has 2 performance requirement. Uh, the performance requirement is lower overall hydropower maintenance expense by 15% within 6 months, and standardized component replacement scheduled to minimize unexpected downtime. For the third quality driver, defect reduction in turbine design. The performance requirement is identify and eliminate root causes of at least 18% of a recurring design defect. For the fourth quality driver, operational process standardization, uh, performance requirement, train 100% of maintenance staff on update SOP within the 3 months. For the fifth quality driver, data-driven decision making. It has 2 performance requirements. Develop a predictive maintenance schedule based on data analysis insight. For the second performance requirement, implements SEADA, supervisor control and data acquisition system to collect real-time turbine performance data. For the sixth, resource optimization, the performance requirement is shift 13% labor hour from the unplanned repair to efficiency action tasks. And for the last quality driver is stakeholder engagement. It has 2 performance requirements. Establish collaborative partnership with hydropower expert to pilot design enhancement, and conduct regular stakeholder review to track progress towards Six Sigma goals.
Talk about Ishikawa diagram, and Ishikawa diagram used to analyze the root causes for defects in turbine operation, and we categorize them into 6 factors: man, machine, measurement, method, environment, and materials. So these key findings include insufficient training, awareness among personnel, outdated turbine technology, inaccurate energy sensors, and the structure analysis from Ishikawa diagram enable us to pinpoint the specific areas for the improvement, and it gives us some methods to overcome the defects, such as enhancing training, upgrading equipment, improving material quality to optimize the mine performance and system reliability. Metric analysis. So this bar graph illustrates the trends in the turbine operation defects over 5 months. So in January, we observed 180 defects with 5.1 defect rate, which dropped to 150 defects in February, the lowest. However, the defects rose to 200 in March and peaked in April with 280 defects and a 6.2 percentage of rate. In May, defects decreased to 230, but the defect remained high at 5.8%. So this fluctuation highlight the need of consistent quality control and maintenance practice to stabilize the defects rate and improve system efficiency over time.
Right, my name is Shafiq bin Said Ibrahim and my metric number is MA23070. So I will continue for the Pareto analysis and baseline metric parts. So the Pareto analysis conduct as a part of this project identify critical area of inefficiency within renewable energy system at Malaysian University. So the analysis categories define into 6 primary area, which is outdated infrastructure, improper energy monitoring, lack of staff training, inefficient energy distribution, maintenance delays, and seasonal variability. So outdated infrastructure emerged as the most significant contributor, accounting for 30.3% of the total inefficiency, followed closely by improper energy monitoring at 24.2%. So combine these two factors constitute over 54% of the observed inefficiencies, clearly highlighting their dominant impact on the overall system performance. So this insight emphasize the necessity of prioritizing intervention in this area to achieve meaningful improvements. Specifically, modernizing infrastructure and implementing advanced energy monitoring system are critical for reducing inefficiency and enhancing operational efficiency. So by addressing this key contributor first, university can expect significant progress toward achieving their sustainability and energy efficiency goals. A deeper analysis of the root causes of inefficiencies in the renewable energy system reveals several underlying issues. The root causes analysis identify insufficient training and awareness among staff as the primary contributor, accounting for 25% of the total inefficiencies. This was followed by outdated or inefficient equipment, which contribute 20%. Other notable causes include the lack of real-time monitoring with 15%, inefficient energy distribution 12%, and seasonal variability 10%. The remaining inefficiencies were attributed to low quality material and miscellaneous minor causes. These findings underscore the importance of addressing training gaps and updating equipment to mitigate the inefficiency in energy management system. Comprehensive comprehensive training programs can enhance staff proficiency in operating and maintaining renewable energy system, while investment in modern, efficient equipment and real-time monitoring technologies can significantly improve energy efficiency. By targeting these high priority root causes, university can develop a robust energy management framework that support long-term sustainability. So the baseline metric for this project provide a clear picture of the current performance level of renewable energy system in Malaysia University. Key performance indicator include the defect per unit DPU of 16.5, defect per opportunity DPO of 0.825, and DPMO, which is defect per million opportunity, of 825,000. This metric highlight substantial inefficiency in turbine operations, as evidenced by the high defect rates. So the data serves as a critical benchmark for measuring the impact of future improvements. By identifying and quantifying existing issues, the baseline metric enable a structured approach to monitoring progress. They emphasize the urgent need to process optimization to reduce defect rates and enhance system reliability. Addressing these inefficiency will not only improve energy output, but also contribute to more sustainable energy practices across university campus.
Next, I will present CPOP. CPOP diagram is the process map which listed out suppliers, input, process, output, and customer of the process. In this diagram, the input and output variable are listed out, and they will be used at the next step, which is causes and effect matrix. Alright, for the suppliers in our group CPOCs, turbine manufacturing, maintenance team, and renewable energy consultant. And for the input, we have 5 input. For the first, turbine design specification. Second, SIT maintenance schedule. Third, energy output data. Fourth, spare part inventory. And the last one, university energy requirement. And for the process, we have 5 process. Uh, First, design evaluation, and then you go to operational analysis of turbine, and then maintenance procedure review, and root cause analysis for operational efficiency, and the last process is implementation of defect elimination strategies. So for the O output, we have 3 points for output: exchange energy production performance, improve turbine maintenance schedule, and reduction in maintenance cost. For the last one, customer C, we have 2 customer: university energy stakeholder, student and faculty benefiting from consistent energy.
So next is the cause and effect metric. The cause and effect metric is a tool used to identify and prioritize the critical process step that influence key output variable based on their importance to the customer. We will choose the critical input variables which influence the most to the defect output towards the process. Maximum score is 218, top quota is 54.5, selection range is 163.5. The method of third quartile approach is used to choose the input with the selection range from the score between 163.5 to 218. 3 input we choose is turbine design specification, existing maintenance schedule, and spare part inventory.
For the measure phase, I did the failure mode and effect analysis. By using the FMEA approach, we analyze the potential failure modes in turbine operation to prioritize the improvement. So the key areas include turbine blades, bearings, sensors, maintenance procedures, and control system. For instance, blade cracking caused by material fatigue at a high risk priority number of 240, which was reduced to 45 by switching to higher grade material, like bearings with excessive wear at the initial risk potential number of 96 reduced to 48% by optimizing the lubrication. So overall targeted action like advanced training, regular inspection, system upgrades significantly lower the RPM values, enhancing operation reliability and minimizing the downtime.
Now I will continue with the normality test. In this project, we use a normality test to assess whether the generate defects data following a normality distribution, which is essential for applying various statistical techniques in our analysis. From the descriptive analysis, we observe the mean, mode, and median all are relatively close to each other, suggesting a statistical distribution. The standard derivative of 2.55 shows a moderate separate of the data around the mean. The histogram reveals a roughly bell-shaped distribution, which visually supports the idea that the data is approximately normal distributed. The normality test also includes a p-value calculation, with a p-value of 0.96, which is well above than the 0.05 threshold. We can confidently conclude that the data follows a normal distribution.
The process capability test conduct during the measure phase of this project aim to evaluate the alignment of defect rate with customer specifications. So the analysis begin with a run chart which plotted defect data against the upper and lower specification limit 10 and 2 respectively. The chart revealed that all data points fell within these limits, suggesting no special cost variation in the process. Using the collected data, key statistical measure were calculated through Excel, Microsoft Excel. The mean defect rate was determined to be 6 with a standard deviation of 2.55. Based on this data, process capability indices CP and CPK were computed using the following equation lah. So this calculation was supplemented by Z-score and sigma level analysis, providing a comprehensive assessment of the process performance. So the finding from the process capability test highlight significant gaps in the current energy management process, with CP and CPK values both below 1. So the process is classified as not capable of meeting the desired specifications. So the calculated sigma level of 1.57 further underscore the need for improvement, as it falls well short of the Six Sigma benchmark of 3.5 defects per million opportunities. This result indicate that the process lacks the precision and consistency necessary to achieve optimal performance. To address these shortcomings, targeted efforts must focus on reducing variability and improving process stability. Strategies such as upgrading outdated equipment, enhancing maintenance protocols, and adopting advanced quality control measures can significantly enhance the process capability. So by implementing these improvements, university can move closer to achieving their sustainability and energy efficiency objectives.
Alright, now I will to present engineer and society issue in study problem, societal health, safety, legal, culture issue, and the consequent responsibilities relevant to professional engineer practice. So this project aims to enhance renewable energy efficiency in Malaysian university, facing operational efficiencies and high maintenance costs for exciting hydropower system by applying Six Sigma methodologies. The goal is to achieve a 10% improvement in energy output reliability and 15 reduction in maintenance costs within 6 months. The process involves definiting the problem, measuring current performance, analyzing root causes, implement improvement, and establishing control mechanism. Key steps include data collection, root cause analysis, solution development, pilot testing, and continuous monitoring. The project emphasizes sustainability, legal compliance, and culture sensitivity, ensuring alignment with border environment and community goals. Uh, Through structure based of defined measure, analyze, improve, and control DMAIC, the project seeks to optimize turbine operational and design while engaging stakeholder and fostering a culture continuous improvement.
So in conclusion, this project tackled the inefficiency in Malaysian University hydropower system aligning with SDG 7 for clean energy. And in defined phase, we use Ishikawa diagram, Pareto chart to identify the problems. And with the data-driven analysis, we improve the system performance, reduce defects, and enhance energy reliability. And it contribute to the sustainability and energy efficiency goals. Thank you.